Last time I talked to you about my work on voice and Parkinson's disease, and I was presenting this with my colleague Newton Howard, who is also a professor at Oxford. Today, I want to be focusing on a different aspect of my research, which is essentially focusing on wearable sensors and smartphones and smartwatches to assess longitudinal symptom severity. And I'm going to be touching on certain different applications and projects we're working on, primarily in mental disorders, post-traumatic stress disorder, and stroke. If we step back and look at the big aim and research vision of my research group called DART, what we try to achieve is address unmet clinical needs. And we achieve that using lots of different ubiquitous sensors and data. As I said, a lot of my work is on the basis of voice analytics, and increasingly I've been focusing on diverse modalities, including EEGs, smartwatches, smartphones, and the lots of interesting information we can actually extract from those sensors. And the beauty of that is that most of these assessments take place passively. So whereas with voice, someone has to, at least in the kind of analysis I'm doing, pronounce a stem vowel, here all the data collection takes place passively. So someone just remembers to wear a smartwatch, or they naturally interact with a smartphone, and we get all this information that we want to be processing on the basis of someone simply interacting with the device without doing something per se specific for the analysis of our studies most of the times. And ultimately, the aim of what we're trying to achieve is assist experts make better informed decisions. So we do not try to basically take the work of clinicians. We try to increase the capacity they have to make their work better. We try to help them make assessments and diagnosis better, or having more tools to assess this rather than a single snapshot. And of course, we try to help them also in terms of longitudinal monitoring. The aim of everything we try to achieve in terms of the monitoring is to facilitate frequent and passive monitoring as much as possible, which gets down to each individual person. And we hope that by using all these ubiquitous sensors, which are increasingly affordable, then hopefully this technology we have is going to be applied at a large scale. So the first project I'm going to be talking to you about is my work on mental health, along with a couple of colleagues, which has been taken by the Oxford NHS. So the current problem that we were facing when I was talking to a couple of colleagues who are in psychiatry is that if someone is worried about potentially having a mental health problem, or even after they have been diagnosed with a mental health problem and they're going to be monitored, in practice, they would only get a snapshot of the clinician's time. So they can only see the clinicians usually for 20 to 30 minutes. They have to be physically present in the clinic. And as you can imagine, that can be quite challenging for people who might need to take days off work, or their carers need to go with them. And of course, it's really cumbersome for those who do not live in the main city centers, so those in rural areas, basically. Another problem with mental disorders is that frequently these have to rely on the patient's own self-recall. So I don't know about you, but if you were to ask me if I was anxious or how well I slept 3 months ago, that's something I probably cannot tell you accurately. And yet, this is what the state of the art is in mental disorders. My colleagues have introduced some new ways that they use to assess all these symptoms in paper-based form questionnaires. And of course, so that's quite useful, and I'm going to come up to the point with certain problems with that approach. The other key thing that you have to realize with mental disorders and other neurodegenerative disorders as well is that unfortunately there is no ground truth. There is no objective way that you can assess on the basis of some blood test or some different biomarker. So you really have to rely on the experts to assess how things are progressing, to assess the symptoms and assess any interventions that might be happening. And quite crucially, if you were to bring 2 trained experts in the room, they would not necessarily agree. In fact, for certain cases, they might agree only about 60 to 70% of the time. So that gives rise to what we call the inter-rater variability. So that's when we come in. The first thing that we discussed with the experts was, instead of having problems with recall bias, and instead of having paper-based forms, which unfortunately we know that clinicians would not fill in time when they have to, we propose to have frequent timestamp self-reports. And as you can see, this is something that fits on a smartphone screen. So we can get all the items, the key items that we wanted for the participants' self-assessment of the symptoms in a single screen. And you can see it only takes about 10-15 seconds once you get used to it. So it's a Likert scale where basically on the left-hand side, it means no symptom. On the right-hand side, it means very much in terms of that particular symptom. And it's very easy to click and identify what you're studying on that particular day. And then on top of these questions, which have been very well established and used in psychiatry, we said we're going to offer also an objective assessment on top of the existing tools. So we're going to complement experts' opinions also with the smartwatches and smartphones. So probably have seen all these kind of different devices. So that's the original Fitbit that you can see here. That's the Genie Active, which I'm going to be talking to you about. Here we're recording ECG and heart rates as well. With a smartphone, you can get information about the activity and social interactions. You can get information about how frequently they talk on the phone, have on the battery. We can get, as I mentioned before, the classical questionnaires that have been established and widely used in psychiatry. And at the end of the day, what we're trying to offer to experts is a continuous personalized monitoring down on a single daily basis at much finer resolution than it's currently possible. And of course, by doing that, we're trying to objectify mental health by offering all this additional array of information on the basis of the passively collected data from sensors. And at the end of the day, we're going to develop tools that are down to each individual, so you can identify characteristic patterns for certain people. So, for example, I might be a fairly miserable person. I might be going to sleep quite early on, whereas perhaps blood might be much more active. Now, what we're trying to capture here is a change in the personalized patterns. So, if you were to see me going out and partying very frequently, that's probably a change of my normal patterns, and vice versa, perhaps. If Vlad, who is usually flamboyant and very keen to go and socialize with people, if he's not making many phone calls, if he's not acting socially and so on, that is a change in his normal patterns, and that could indicate some sort of pathology. So that is the key of what we're trying to achieve. We try to get all the sensors, the patient self-reports, the information we can get from the sensors, and identify what is the baseline for each individual, and then try to see longitudinally how that might change. For this particular project, we focused on people who were diagnosed with bipolar disorders, borderline personality disorders, and we had some baseline health controls because we want to ensure that what we're trying to quantify is over and above what the health controls variability might be. And we used a lot of different questions which have been very well established in clinical practice and collected data for at least 3 months for all the participants. And for most of the participants, we actually collect data on a daily basis. That's crucial for a full year. So we start our work by essentially using the very well established questionnaires like this quiz, which is assessing problems with depression. And it's a fairly extensive self-report scale, which comprises lots of questions. So we developed a new questionnaire, this mood zoom that you can see on the left-hand side that fits on the size on the screen of a smartphone. And we can get the same, but we can hope that we can get the same kind of underlying latent variable information. So the psychiatrists proposed a couple of key items that we care about in mental disorders. And the first aim that we aim to achieve was basically establish how well this new questionnaire relates with the preceding validated questionnaires. The other thing I should probably say is that the validated questionnaires would only be filled out once a week, whereas we aim to get things at a much finer resolution. And if we want to get all this fine daily resolution with questionnaires, we needed to ensure that people would only spend less than half a minute to really fill it in on a daily basis. So what you observe here is a couple of different questions we have for each participant. You can see that for this particular participant, let's call them S6. He's been diagnosed with bipolar disorder, and we monitor them for a full year. And we do it for a couple of different questions. So the first one is quantifying manic symptoms. Second one is depression, anxiety, quality of life. That's the new daily questionnaire that we have. Again, all these 4 questionnaires take place on a weekly basis. The last one is on a daily basis. That's why you're going to see it's much more densely populated. What you see with colors is essentially what experts identify as episodes. So, for example, someone here had a manic episode, someone this duration had a depressive episode, and so on. And you can see there is a fairly clear pattern of bipolar disorders where you have mania and depression. So you can see this person during that period is manic and depressed, vice versa. He's depressed, manic, depressed, and so on. So in this period where he's neither manic nor depressed, it's what we call euthymic. So the first thing we want to assert is essentially how well our new questionnaire can capture this variability and identify what's happening with individuals. And we managed to see this quite accurately. We managed to extract information and match to what we call the latent variables and identify a robust subset of those items on the original questions that basically match very well with the new mood zoom questionnaire. And identified basically that there are 3 key characteristics that we aim to be capturing in primarily bipolar disorders and borderline personality disorders. And these are the anxiety and sadness aspect, positive affect, positive feelings, and the third one is irritability. The great thing is that these came automatically from the processing of the data, from a data science perspective, and they were fully validated by the psychiatrists that we were collaborating on. The next thing, moving beyond someone that is energetic and someone has to physically go in and actually self-reporting the symptoms, is capitalized on wearable devices and smartphones. So this is work that one of the PhD students we had in the group did. Nick, he's done some really good work in terms of processing data that we get from GPS from the smartphones. And the kind of information we managed to get was that, for example, during the night, where the phone sits, that's what we would assign as home for a particular participant. So that would have the coordinates of 0.0. And then we could try to identify patterns of movement, patterns of GPS variability, and basically match it down to symptoms in terms of depression. So you can see here that we can actually differentiate very well people who are health controls versus people who have bipolar disorders and they are depressed. So it's quite important that we published this work back in 2017, that we can use information passively collected. Someone just has to have the phone with them. We don't have to actively engage with it. And just on this passive information with the geolocation, following this GPS tracking, we can actually identify if someone is having a week that is characterized by depressive episodes, as the psychiatrists would call it. Moving beyond that, another PhD student we had in the group, we worked on quantifying circadian variability and mood. So again, it's in the same kind of project. So this time, Oliver focused primarily on assessing sleep and heart rate using the Proteus patch. And what we managed to demonstrate is that essentially we can mine information, the heart rate variability, matched with sleep characteristics and acceleration, and essentially match it to mood. And we published some work back in 2018. So the interesting part here is that, as you can see, you can have the classical pattern in terms of the acceleration on the top two panels. You can have information in terms of the heart rate. You can fit certain characteristic waveforms, and from that you can extract clinically useful features, which ultimately, through certain processing, can be mapped onto the severity outcomes that we've talked about before. So just again, on having some passive information collected from the Proteus patch, you can get the raw data in terms of the acceleration, in terms of the heart rate, and match it quite accurately to symptom severity scales. The next part, we've been working also with the Smartwatch. So the Smartwatch, if you were to see the raw data that you can get, is actually in a hexadecimal format. So it's actually very difficult to interpret and understand what is happening in the hexadecimal. But the part that we're doing, and that's part of my work, is essentially trying to map these hexadecimal original values down to the acceleration of what is being recorded through the acceleration. And then, based on some smart signal processing algorithms, automatically identify, for example, sleep patterns, and what you see here with green. And you can concatenate this along all the different dates that you monitor some participant and essentially see the variability in those patterns. So we process those patterns, we extract the features, and we characterize each individual and the variability long-term for the duration they've been wearing the watch. Here's an example that focusing on a single participant, this is a health control person. So what you can see is that we follow a person for 24 hours, that's the actogram, and that's the second 24 hours. And if you see the second half of its panel is essentially repeated beyond. The reason we do this with the actogram is because experts have been very used to seeing what's happening around midnight for a participant. So you can see that we have the midnight and we want to be assessing, for example, if that particular person has been in bed or not. And the interesting part here is that we develop the algorithms to automatically assess sleep, and you can see the variability when someone goes to sleep and when someone is waking up. And the base of additional patterns, you can try to quantify, for example, the stability, the variability, or the amplitude. And essentially, these are what we call the patterns from which you can characterize down each individual. So you can imagine if I'm wearing the watch for a month, you can assess my interdaily stability, my variability, my amplitude rate, lots of different metrics that we extract there. And essentially, you can assess the fragmentation of my circadian rhythm, the rhythmicity of my circadian rhythm. You can see the movement if there is a repeatability, and so on. And once again, the interesting part here is that by processing the information you can get from the smartwatch and what we've called the actograms, you can actually match it down to the questionnaires. So for example, you can have this participant, you can extract some features on a period that that participant was, as you can see here, having manic symptoms. You can have the information that someone was wearing the watch, but they were having depressive symptoms. You can extract the features in both ways, for both different durations, and actually try to identify when someone is euthymic, when someone has manic symptoms, and when someone has depressive symptoms. Again, I emphasize everything is done passively. So all you have to do is wear the smartwatch. You do not have to interact with it. All the information is collected based about 3D acceleration, wrist-worn temperature, and ambient light. And then we develop the algorithms to process the data and actually match it to mood patterns. Let me try to move on a different topic. Once again, we stay on the limit with the same kind of wearable technology, but I'm going to be talking to you about the effects of how we can achieve monitor a very different kind of disorder, and that's the post-traumatic stress disorder. So that affects many people, primarily perhaps people who've been in war and have had some severe events that they have witnessed, women who were raped, and so on. Quite interestingly, not everyone has experienced severe event, severe traumatic event to develop PTSD. It really depends on certain other factors. Once again, similarly to what we discussed previously about mental disorders with bipolar disorders and borderline personality disorders, PTSD requires a person's physical presence in the clinic in order to be assessed, in order to monitor symptom severity and adjust treatment. And once again, we have all the classical problems that we have with this kind of neurodegenerative disorders and mental disorders. The assessment relies on recall from the participants, which of course introduces a recall bias and is subjective. And once again, there is no ground truth. You rely on the expert psychologists or psychiatrists to make a diagnosis. And again, there might be disagreement between experts. So what we're trying to offer again is a tool to improve the way that people have access to data and make better informed diagnosis on the basis of some additional information that is presented to them on top of what the patients themselves recall. So in this particular project, we had 42 people that were diagnosed with post-traumatic stress disorder. We had 42 traumatized controls, so people who had experienced some traumatic event, but they were not actually converted to develop post-traumatic stress disorder symptoms, and we had health controls. And I emphasize that is a particular strength of this particular study that we had. non-traumatized controls, because many studies only compare people with a post-traumatic stress disorder and health controls. And once again, they wore Smartwatch that we gave it to them for a month. They completed sleep diaries and a question which assesses sleep, which is one of the key characteristics, key symptoms that we observe in post-traumatic stress disorder. And the key part that we achieved in this project was that we assessed people before treatment and after treatment. So they wore the device, they wore the watch. We passively collect information from them in terms of watch. We got the sleep diaries and the questionnaire, and we did it a week before they actually were to receive a specific treatment for this condition, and then a month after they received this condition. So we can basically assess what is happening objectively. I stress again, all the assessments so far in mental disorders, PTSD, and so on, are on the basis of expert opinion. And here we offer for the first time, as far as I know, the means to objectively assess if treatment is working. And you can imagine the implications this may have in terms of, for example, insurance companies and experts making better informed decisions if something is working for this particular individual, or if it's not, you may need to adjust medication or treatment. Before we proceed any further, I have to ensure that the algorithms we assessed for sleep were actually generalizing well. So I took an algorithm that was very widely used in the research literature by Vincent Marquis. He's done some great work in terms of figure processing. Most of his work has focused on health controls quite naturally, and well, when we start doing the analysis, we tend to focus on health controls for the analysis we do. But quite crucially, we have to go a step further and try to validate and extend the algorithm we have in pathological cohorts, in groups with certain disorders, definitely with sleep disorders, and see how the original algorithms would generalize. And you would see, perhaps unsurprisingly, the algorithms do not necessarily generalize very well from health controls down to people with certain sleep problems. And vice versa, I developed some algorithms for processing actigraphy data and correctly detecting sleep onset and sleep offset, so you can actually get it down to fewer minutes. Let's probably emphasize that this is minutes deviation from the ground truth. So for example, you can see that if you have health controls or non-traumatized health controls, we can actually get, for example, the sleep onset with only 12.5 minutes difference than the ground truth that people have self-reported. And the offset, that's actually a much easier problem, because someone is getting off the bed and they start moving, so it's actually much easier to detect when someone is has woken up. And quite instantly, you can see that we can do it much more accurately compared to the existing algorithm in the literature, particularly for the case where we have people with certain disorders. And this work that I published earlier this year. Interestingly, then, we can proceed to extract certain characteristics on the basis of actigraphy, as I was mentioning before, and try to assess and establish whether there are differences between those groups. So we've done all these analyses, and we can demonstrate that on the basis of even single-based characteristics, you can observe meaningful and statistically significant differences between pairs of those groups. So it's quite crucial that, for example, some of those correlations are indeed quite strong. For example, you can see that this particular feature we've extracted, it's the mean diurnal skewness, is essentially matching very well to identify if someone is a control participant or a PTSD participant. So you can imagine that this could be used, for example, in terms of assisting diagnosis. The next part, which is something we're working on towards publishing these days, is essentially about comparing the actigraphy means before and after treatment. So you can observe a participant that has been diagnosed with a post-traumatic stress disorder. We can observe the raw signal modalities. So you can observe, for example, the movement, the fluid acceleration, the temperature we have for this particular participant, the wrist temperature from the watch, and the ambient light. And on the basis of that, you can extract the actogram, which is again presenting information in convenient format. We can extract the features and have extracted more than 60 different algorithms that characterize each individual for the time that they wore the watch. Then we have the case where they have been treated for a week. And then after that, once again, we monitor the participants, so we have the raw comparison in terms of the raw data, the extracted features before and after treatment. And what we've managed to find is that essentially actigraphy can be used to differentiate people and identify the effects of certain treatments that are used for this particular field. And I stress again, it's the first time that we can objectively assess the effects of a treatment. And indeed, we find that for certain individuals, certain treatments might work, and that's quite obvious in terms of the data we observe, in terms of the patterns we observe. For certain individuals, things might not work. So it could be used, for example, to objectively inform the clinicians that this particular treatment might not be optimal for this particular person, and hence something different needs to be tried. Let's move on a different project. Once again, we stayed in the limit of working with wearable devices, but now we move on to people with stroke. So we wanted to assess people who have been diagnosed with, who have had a stroke episode, and we want to monitor them and identify what is happening before and after treatment. So it was a pilot study. We didn't have too many participants. We only had 27 participants, so everything we have found should be interpreted quite tentatively. But we're actually working to try to generate many more samples and try to record many more participants. We do not have normative data either. Similar to our previous study, we had a smartwatch that collects passively data. Once again, the same kind of idea like the PTSD project. We had questionnaires that people are to self-report on their anxiety and fear. And we collected, once again, assessments before and after treatment. So once again, we try to objectively assess what is happening in terms of treatments using some objective data. And you can see here what people have self-reported in terms of having some different treatments. So task CBT and task relax. These are different ways that you treat the groups. We model them. You can see you have the baseline, week 6 and week 20, and you can observe how things might differ in terms of this longitudinal progression. And you have different questions. So the first one, for example, is quantifying anxiety. The second one is quantifying fear. And you can see, once again, how these features might be captured in terms of the wearable information you can get. So what I'm presenting you here, for brevity, because I don't want to overcrowd this slide with multiple plots, is only information about what happened at time 2 that the participants were wearing the watch. And you can see essentially the effects of different treatment, how these are mapped down to the different groups. So for example, you can see the stability that people might exhibit in the task CBT and the task relax, which you see here, for example, is not very different. Whereas other features might be more informative in terms of portraying this difference. So, as I said before, we extract lots and lots of different algorithms, and then we aggregate all this information from the different features to try to map and objectively assess the effects of the different treatments. And that's some work again that we published, I think it was around April, May this year. And then one of the students that was working with me over the summer, he did some quite interesting processing where he focused exclusively on sleep. And the reason we did that was because we want to extend our findings from PTSD previously, and we want to assess here how important sleep is for assessing people with a stroke. So essentially, he developed some algorithms to identify what we call as passive sleep and active sleep on the basis of particular movements during those 8 or 10 hours that someone is sleeping. And essentially, we could try to identify those predictions, those assessments that we had from experts in terms of whether something was an ischemic stroke or a probable brain injury. So using all of these sleep-based characteristics that we extract from the actigraphy and using some very well-established approach for model validation, we could basically get a very accurate estimate in terms of the different predictions. So you can see we could get it with about 8.5 accuracy. And again, I need to emphasize all that is just on the basis of having information you can extract from the smartwatch. We do not get there to use additional information you can get to aggregate from potential additional sensors or the participants' own self-assessment. So you can see how this can be used for a passive tool that can inform clinicians to make better informed decisions. If I can try to summarize the 3 projects I've described to you, I hope I've managed to convince you that data that is actually fairly easy to collect and quite importantly, just passively collected data on the basis of smartwatches or smartphones, we can actually get clinically useful information. We can actually use this information, process it using some new algorithms and some machine learning tools, and actually match it down to the scales that the clinicians use. So people can just stay at home, collect the data, send the data into the clinic, can process the data and provide it in some format that the clinicians can easily digest and understand, and basically try to come up with the optimal course of treatment on top of the information that the patients provide to them. I think generally there is an understanding that we're moving much more towards passively collected data rather than all these self-questions that it's really cumbersome for participants, and it's quite challenging to ask people to fill in all those questionnaires at the resolution that is quite desired. Overall, I've been working in this field for a couple of years, and I think it's really fertile for developing new algorithm tools. It's really a goldmine for all people with a data science background. And of course, we really need to be working with the experts to make some key breakthroughs and develop better solutions for the people who suffer and the NC's patients. And isn't that what we all want? Thank you very much.